So we're now going to take our understanding of RC circuits, the last final step. We still want to be able to use simple relationships like Ohm's law when we're talking about our AC circuits. And so we're going to now look at this supply voltage, and we recognize that the resistor voltage is always going to be equal to IR. Whatever I is, VR is going to equal IR. The capacitor across the voltage we just found out is going to be equal to IXC, where XC is the reactance, remembering that XC equals 1 over omega C. Okay, and we're just going to put that to the side because that's not essential right now. Here's the interesting thing. If that's the case, and that's the case, then the supply voltage must follow a similar relationship, and it turns out that it does. We can actually say, well, the supply voltage is going to be equal to the current running through it times by something called Z, impedance. Okay, I know you're a bit sick of all these new things, but we've got resistance, we've got reactance, and now we have something called impedance. And why it's called impedance comes from the idea that this is what limits the current flow. This is a different way we've talked about it. Up till now, we've always talked about converting electrical energy into other forms, but impedance is another way of thinking about it. Z, the impedance, resists or impedes or reacts to the flow of the current. Okay, so the interesting thing that we can do is we can find Z in terms of R and the reactance. Okay, because if we know that this is true, okay, we should then, it follows, that we should be able to take this diagram and we should be able to say, well, okay, if that's the case, if this vector here equals IZ, I is common to all those things. So therefore, R and XC should add together to give us Z. And they do. So we can use Pythagoras to figure that out. So what we find is eventually that Z equals the square root of R squared plus XC squared. Remembering, of course, that XC can be related to the actual capacitor using 1 over omega C. So you can see that as you change the frequency, you change the reactance, therefore you change the impedance of the entire circuit. So you can use frequency as a way of tuning circuits to do what you want them to do by changing the total impedance of the circuit. And this is just a really nice, simple way of explaining how frequency changes the response in a circuit using impedance, which is measured in ohms, by the way. We can use Ohm's law, and we can also, in the back of our heads, always have the idea that the supply voltage, the resistor voltage, and the capacitor voltage are always changing with time using those varying sine curves. But we don't need to consider those sine curves if we can deal with it using ideas about impedance.